So we have Costa, coming from the University of Aveiro and from his CD. I saw you were very productive in book chapters and lots of students. And today we talk about microwave radiation technology and material processing.
Thank you, Professor. So, yes, sir. Okay. Thank you. First of all, thank you for inviting me for this presentation. So I will try to talk about microwave, a little bit different from the first subjects. So I will present two different cases. One is low power microwaves. Let's see, this means about milliwatts that you use in metrology. And high power microwaves that you use in heating, let's mean something like kilowatts. Okay? So, in this graphic we see total time as a function of frequency, so microwaves were more or less here, okay? In this region. And in this region, we have here bound water and free water, okay? And free water, absolute time is really higher than bound water, okay? So we have a difference in this region, okay? Where we know that free water it's really higher than bound water. So we will try to apply these concepts to the seed. This is a tomato seed, okay? And we can imagine that the seed is a complex material. And this seed has three different, let's say, components: the matrix, okay, the bound water, and the free water. And we can use this very simple inner law that says that the absolute prime, and also for sometimes the same total. It is absolute prime, the matrix multiplied by the volume fraction of the matrix, absolute prime of bound water, volume fraction of the water, and also absolute prime of free water, volume fraction of free water. Okay, this is a very simple assumption. So what can you do? You extend calculus. So we can see this information from the industry, and we know that, for example, so here we have the live seed and the dead seed, two seeds, okay? So here it is the matrix, okay? The matrix we have 80%, this is the matrix, okay? Also involves live seeds and dead seeds. But when we have a live seed, we have 18 bound water and only 2 free water, okay? And when the seed is dead, it changes, so we have 2% of bound water and 18 of free water. This is changed, okay? And also, if the seed is dead a lot of time ago, actually we have no free water, okay? So with this law, we calculate the absolute time for the live seed and for the dead seed using these percentages, okay? Then we have, in this case, for example, for the total that we calculate for a live seed, we have 62, okay? And for the dead seed, we have, in two cases, there are two different situations, 2.28 or 541. That means, or it is really very high compared with this one, or it is very low compared with this one. That means, if you have a live seed, we have intermediate situation. If it is dead, it is very high or very low. Okay? So then we use this setup. We publish the seeds, okay, in a constant temperature and humidity, okay, in a container during 1 week. Okay? Then we took one seed, another seed, and we want to try to measure exactly the total time for each seed, and then compare with the theoretical values that we calculate to, let's say, to try to understand if the seed is there or it is not. Okay? Then use this system. If this is a resonant cavity, okay? We have resonant cavity. We have here an antenna this side and an antenna this side. We put here a weight, okay? In this antenna, it propagates inside this cavity, okay? And then we collect here the reception. And we measure simply the S parameters. In this case, we measure the transmission of the cavity. When the cavity is absolutely empty, nothing inside, we have resonant frequency, okay? You know exactly resonant frequency of this cavity. So, what happens? When we have an empty cavity, we have something like that, okay? This is the transmission of the cavity, okay? There's a peak. And here we have the resonant frequency, F0, okay? So this distance is the reverse of the quality factor, okay? If this is very large, the quality factor is very poor. And what happens? When you put something inside the cavity, that means here we have the cavity, we have the antenna, another antenna, here we have a hole, and you put something inside the cavity. And what happens? The electric field will be propagated, and then this transmission will be changed. And what happens? When you put something inside, the peak goes to the left. This means that the resonant frequency changes. So here I load the cavity, and I see here the new transmission of the cavity. What happens? If T0 changes for this position, okay, so that means the port goes to the left, the resonant frequency decreases, and also what happens? The quality factor also decreases. So that means this distance here, okay, decreases. Increases, okay? And there is a theory we call the small perturbation theory that calculates x to the power prime and x to the prime as a function of these changes, the change of the frequency and the change of the quality factor, okay? So x to the prime is, in this case, proportional to delta f. Delta f is this distance, okay? That means the resonant frequency. This is the volume of the cavity, the volume of the sample. This is this f0, okay? And this is a constant that you can calculate. So if you measure delta f, you can calculate x to the double prime, okay? Then we also can calculate x to the double prime using this delta of this distance, okay? Okay, that means when this increases too much, this means that x on the double prime is very high, okay? So what we can do in this case? So we make a measure of empty cavity, then we put a seed, okay? This is the seed number 1, okay? Then we put empty cavity, seed number 1. Empty cavity, seed number 1. Empty cavity, seed number 2, okay? Empty cavity, seed number 2, okay? And you make this, okay? And so this distance here is delta f, okay? This is the difference in the resonant frequency. So this is proportional exactly to absolute prime, okay? Also, we make this with the change in the quality factor, and then we try to calculate absolute prime. Okay? So, in this case, we calculate absolute prime. Why? Absolute prime, let's say we saw that the absolute prime is more sensitive, okay? So it's more accurate. So, what we do here we have absolute prime, in fact, okay, this side, and here we have the weight. Because why? Because the totals is not, they are not exactly the same. So we are normalizing, let's say, this data. So here we have 106, okay, here. Oops. Oh. So we have here, for example, seed 21, seed 11, okay? And we know that in this case we have only 5% of seeds that are dead, okay? So we put here this ellipsoid, okay? And outside, okay, are 5 or 6 seeds, okay? What happened in this case? For this seed, for example, 37, the total track is very high, okay? And this one is very low, okay? And this is the normal situation. Means these seeds are there, okay? That are outside of the ellipsoid. That we say, okay, 90% are inside this ellipsoid, okay? So, this is a good criterion to decide, okay, the seeds that are outside of this ellipsoid are there, okay? This is the first criterion of the communication. So then we try another criterion, that is, we know that when the cellulose are dense, they are more isotropic, okay? That means this is the seed, okay? Tomato seed. This is a tomato seed with their cellulose. That means when they are there, the heterogeneity increases. That means this is more anisotropic, okay? And what is the advantage of measuring in excellent cavity? The electric field is very highly polarized. That means the electric field is always in this position, here. And then we can explore this because we can put the seed inside the cavity and then rotate the position of the seed. Okay? That's what we made. So we have the electric field very polarized inside the cavity. Something like that, okay? We have the seed here, then we turn the seed 1, 2, 3, 4. Okay, and then we calculate absolute time again for these 4 different positions. Okay, and what we see, if you remember, for example, see 37 that was there because it was outside of the ellipsoid. Here it is. Okay, you see, this is a very anisotropic because the values are very different. This one also, for 28, it was outside of the ellipsoid. And also we see that here it is very anisotropic because absolute time is very different when we measure in the 4 different positions. Okay, this means that we can use this second criterion, okay, to eliminate the seeds. And it is curious because the seeds that we eliminate in the first criterion are exactly the same seeds that have this really very high anisotropy. Okay, so this is the first case that we made using very low power microwaves. So we use exactly 1 milliwatts. Okay, so then let's see the second case. High power microwaves. So you know that the distribution, the power dissipated in the electric field is proportional to absolute time. Okay, this means that so this is not important. This is not a magnetic case. So we have absolute prime here. This means if absolute prime increases, the dissipated power increases. This means I can increase the temperature of a material that has absolute prime very high. But the problem is that the penetration depth is the inverse of the conductivity. Okay, the conductivity is proportional to absolute prime. You see, if absolute prime is very high, sigma conductivity is very high, and if this is very high, here the penetration depth is very low. Okay, so that means I want to eat all the material inside of the material, so I must have a compromise between enough penetration depth and enough power dissipated in the material. So this is a simulation. We made this is a simulation. What happens? Here, this is a microwave oven, okay? Here we have a sample. And then we, using the Costa software, we calculated in 3 different points, okay? Okay, here, so this is only half of the cavity. We see 3 points here, okay? And we try to simulate the temperature evolution with time, okay? Of these 3 different points, okay? So we have only 1 magnetron here, okay? So we put here the radiation, the microwave wave, okay? It enters inside, so it reflects in the walls. It is absorbed by this material. Then I see here there are 3 points that are really different, okay? Then we calculate how this evolution with time. So this is the 3 points, and you see after, for example, let's say 40 minutes, 1 point it is something like 300 degrees, and this point it is more than 1000. So there is a very, very high gradient. This means that probably we will have a problem because the temperature is not homogeneous inside this sample, okay? So this is the simulation, okay, that we like to do, and this is real life, okay. Then we put this cup because we are trying to synthesize these materials to cure porcelain, okay. This is the cup we put inside this microwave oven. We turn on, and after a few minutes we see this. Okay, why? Because actually there are a very big gradient between different points at the cup, and this will give mechanical strain, mechanical tensions internal, and as consequence, the material will be destroyed. Okay, so this means that if I am to do this with 1 magnetron, okay, and I treat the material with 1 magnetron, and in the center of the oven, and in this static position alone, this is what happens. Okay, then we try to make some simulations putting several magnetrons. In this case, it is 6 magnetrons. Okay, so we have here a guide wave. Okay, here is a magnetron. 2 magnetron this side, 2 on the top, 2 on the other side. So from this to this, we simply change this magnetron. Okay. So these are in the same position. These we turn 90 degrees. Try to see what happens. If you put all the electric field is like that, and if you put some like that and some like that, okay? And we see actually it's absolutely different the distribution of the electric field. This is the electric field inside the battery. So in this case, for example, see here it is really very, very homogeneous. Okay, in this case. In this case, okay, there are some problems, but it's better than this one. So then we design a prototype using exactly this configuration. Okay, this is our prototype. So here there are magnetron. Okay, here it is the wave guide, and you see this is 90 degrees one from another. Okay. Also here we have here and here, okay, 90 degrees, okay, and so on, and another on the other side. Then we have here some protections because the temperature in interior will be about 1,400, so we must isolate this from the outside. And then we try to put inside the material inside. And okay, this is the results are really very good. Okay, this is a cap and this is a plate. Okay, and you see, okay, it's not top, but it's almost something that you can use at home without problems. Okay, then I have now 30 seconds because the time is running. Okay. And so, conclusions. So, this model theory, this cavity, resonant cavity, it's very interesting to make journals in materials, even in seeds, okay? And finally, it's quite important to homogenize the temperature inside the oven, if not, the results are not relevant. Okay? Then, thank you. Then arguments to the projects that financed, and also thank to my students.